Sunday, June 11th, 2023. You are listening to Weather with Enthusiasm.
This past week, we had portions of Siberia that saw several days with temperatures in the mid and upper 90s. We even had places that went into the low and even mid hundreds. Well, we should say about 103 degrees. These temperatures are reported on CNN, and you could find out more information by going to CNN to find out more of the details. This heat wave did not include the Arctic. As of now, we do not have a heat wave in the Arctic. One of the most fascinating cities in Russia is the city Astrakhan. I believe that's how you pronounce it. It's on the Caspian Sea. And the Caspian Sea is very fascinating. If the Windy.com app is accurate, when it says the water temperatures are up already in the mid-70s, and this is at about 45 degrees north latitude, we're seeing dew points going into the mid and upper 60s in that area, with temperatures also going from the mid-80s to the low 90s. What's very fascinating is that this is another part of the world where you have a very, very harsh winter and you have an actual hot summer. The normal high over there in July, the normal high is 91 degrees.
But what's also really fascinating about the Caspian Sea is that you look at the water temperatures, they're already in the mid-70s if this Windy.com app is accurate. I mean, that's so warm. I really question the accuracy, but let's say it is in the mid-70s. It's only June, and this is a place that has received super harsh winters. And what's even stranger is that as you go south into the sea, the water temperatures actually become cooler. So if all of this is true, the explanation that I have is that if you look it up online, you'll see that the depth of the water is actually really shallow up north. I think they said 12 to 20 feet. But when you go down south, I believe it's in the thousands. The depth is tremendous when you go down south. So it's much easier to heat up shallow water than it is to heat up, water all the way down south. So you have lots of sunshine, you have warm temperatures, even though there was a harsh winter. And in fact, the northern part of the Caspian Sea is the first part to turn to ice in the winter. It's all ice. Once in a while, there's ice in the south part, but it's all ice. That's also because the water is so shallow. But right now, temperatures are already in the mid-70s for water temperatures, and that's already producing dew points in the mid and upper 60s. It's something really interesting, and I would love actually to go there for a year and see what it really feels like to live through a winter there, a summer there. Also, the research that I did shows that Astrakhan actually has hot and dry summers, but from what I see, it looks like they actually have humid conditions much of the time. So that's something which also would need investigation. It's a fascinating sea, the Caspian Sea. It's also the largest inland lake in the world, and the situation is very, very interesting. It's something that perhaps we should research further. There's a lot more to say on the Caspian Sea.
We're going to go into depth as to what exactly happened. Why are these temperatures occurring in Siberia? How does this take place? So, believe it or not, all of this really has to do with your first grade science book. It's on that side of the page where many people have gone through this, where they show a picture of the globe and a flashlight. And the way it works is it basically tells you, for a child, it explains why the days are so long up north and why the days are so short in the wintertime. And in fact, by the North Pole, there actually is no day at all during the winter. And in the summertime, there is no night at all. It also shows you the parts of the world which are getting the most direct sun. And those parts of the world, generally speaking, are the hottest. When you go down into the tropics, any area which is between 23.5 degrees or so north latitude to 23.5 degrees south latitude, those areas are considered the tropics. Miami Beach is very close to that. It has a tropical climate, but it never receives direct sun, therefore it's considered subtropical. So it's any place that receives direct sun at least one time a year has a tropical climate automatically. That area has a tropical climate. Any place which has a tropical climate but does not receive direct sun, that place is called a subtropical climate. Tropical climates are hot and humid all year round. Miami qualifies. Although Miami in the winter, it could get cool at times, it still qualifies for that type of tropical climate. So we're going to call it subtropical for a place like Miami. These things are very simply understood when it comes to the winter. In the summertime, things get more complex. And in order to understand that, you need to do that experiment with the flashlight and the globe, and you'll see that the areas getting direct sun, the areas where the flashlight is shining at directly on the globe, those areas clearly get dark. If you spin the globe, and the Earth is always spinning, so when that city, let's say, reaches the other side, it's going to be dark. When the flashlight's shining on the city, it's bright, and when that city, as the globe turns, and it's no longer by the flashlight, it's within the shadow of the Earth, so it's not receiving any light. The Earth is blocking the sun's light, so there is no sun. So therefore we have night. So places around the equator, places in the tropics, generally speaking, have about 12 hours of daylight and 12 hours of nighttime. These hours do fluctuate, depending on exactly where the sun is, but it's pretty close to 12 hours of daylight, 12 hours of nighttime. Sometimes it might be 13 hours of daylight and 11 hours of nighttime, or vice versa. Things get more complex as you go north. As you see the Earth tilt, if you tilt the globe, you tilt it to your right. You tilt it to your, as you tilt it to your right, that's what happens by June 21st. The globe is tilted to your right just enough so that the sun is shining directly over around 23 point some degrees north latitude. So as you spin the globe, if you do this right, as you spin the globe, you'll see the same thing for cities along 23.5 degrees north latitude. Around there, you're going to see the same thing. You're going to see that there's day and there's night. But if you do this right, which I never did it right until last week, you'll see that the upper latitude, as you go to the top of the globe, it's always light. If you don't see that, it's because you're holding the flashlight closer to the globe than you should be. If you're holding it in the proper distance, you'll see that it's always light up there. And with that, we can now explain why temperatures get hot. We now have explained the summer season and why the hottest temperatures in the summertime do not occur by any place which is getting direct sun. They occur usually to the north. They usually occur in the 30s, about 10 degrees north of where the final tropic area is, about 33 to 36 degrees north latitude. That's usually where the hottest temperatures are going to occur. We have, for example, I think Death Valley, California is on 36 degrees north latitude. That also happens to be an awesome geographical place for the place to get hot, because you have, you don't have humidity there, and it's very dry, and it's a very low elevation. The lower the elevation, the hotter the temperatures are. So Death Valley is really an ideal place, not just because of the latitude, but also geographical speaking, that's the same way. But even if you take away the geographical parts to it, you'll still see that the hottest temperatures tend to occur within that area, maybe a little bit to the south. Okay, now let's just explain this for a moment. So the National Weather Service has something called solar insolation. They discuss something called solar insolation, and we're going to talk about that in just a moment. But first, before we do, we're going to talk about something that will give you a greater appreciation for this chart that the National Weather Service has come out with in regards to solar insolation. And here is the thing. Think about what we just said. Envision an Earth, envision you're in a city which is getting direct sunlight. You're living in such a city. That means at noon or in the summertime at about 1 o'clock, there's absolutely no shadows in this city. There's a time during the day where there's no shadow because the sun is directly over your head. That city, the ultraviolet index, is going to be super, super high. That means the amount of ultraviolet rays that is reaching the surface will be higher in that city than any other part of the world. That puts the skin at risk for being sunburnt. And the EPA, I don't know if it originally started from the EPA or if it's them who's advertising it, but eventually gets advertised from the National Weather Service or broadcasted from the National Weather Service. But the EPA has an index of 1 to 15. Currently it's 1 to 15. Originally it was 1 to 10. That might be important to know for people who were around when the original 1 to 10 scale got put in. People should know the scale changed. It's now 1 to 15. So a number 6 back in the year 1994, for example, I remember when I was in camp, a lot of times it was at a number 6 or number 7. So 6 was considered a moderate level of ultraviolet rays, 7 was considered high, but those numbers are different now. The 7 is now a 9 in many locations. It's up by about 2 in many locations. The ultraviolet index tells you how much ultraviolet rays is reaching the surface. It's based on a forecast. A lot of times, usually when you have clear skies, that's going to produce the maximum amount of ultraviolet rays. Of course, it depends on your altitude. It depends on when you're in the mountains, there's more ultraviolet rays. And when you're all the way down by the Dead Sea, for example, or Death Valley, when you're below sea level, there's less ultraviolet rays because there's a lot of atmosphere that filters the UVB light and even UVA light, I believe, but the UVB light is the one that produces the sunburn. So people are actually safer in regards to the sun and getting a sunburn in these cities which are super hot, like Death Valley, California, or the Dead Sea. Some people say you don't even need to put sunblock lotion on when you're by the Dead Sea. I would be pretty scared to do that, but some people say that the Dead Sea, which is the lowest point on Earth, it's in Israel, it's the lowest point, it's well below sea level, so there's an enormous amount of atmosphere. So despite the fact that it's hottest, the low sea level, but when you go below sea level, it tends to get hotter the lower you go, but in regards to ultraviolet light, it also gets less when you go down there, and when you're in the mountains, there's a lot more ultraviolet light. People a lot of times when they go skiing in the Rockies, I always hear it associated with the Colorado Rockies, but really it's anywhere in the Rockies. When they go skiing, especially in the springtime, people can come back sunburnt. The parts of the skin that were exposed to the sun could end up sunburned. So over there, that's because you're in the mountains. The sun is really strong. It's in the springtime. The sun is really strong. It's not like the winter. And secondly, the snow reflects a lot of, well, let's leave the snow out for now. I do not know the effect that the snow has on the ultraviolet light. I used to think that it reflected the ultraviolet light, but it's possible it just reflects the light. So, but either way, a person is better off putting on sunblock lotion, even though it's 0 degrees out. when they're going skiing in the springtime. So it's not dependent on the temperature. For the most part, it's not dependent on the temperature. There is, I should tell you, meteorologist Tom Skilling mentioned that temperatures could play a role at some level. I believe it's the human sweat that could magnify it on some level. So there is something to be said about when there's hot weather, the ultraviolet light hitting your skin might be slightly more. That's possible. It's difficult to find information in regards to that, but that is a possibility. But the main thing is the strength of the sun, how far away you are from the sun, and not the temperatures. That's the main thing we're dealing with. Okay. So with that being said, think about for a moment, if you wanted to figure out how strong the sun is in a certain city, and you have easy access to information such as ultraviolet index. It's available on almost every weather app. So what would you do? You want to figure out how strong the sun is. So what I used to do, it's very simple. How much ultraviolet rays does it say it has on a clear day? Look, on a clear day, the ultraviolet index in this city is a 9. St. Louis, Missouri, June 21st, ultraviolet index a 9. Maybe it's even a 10. Chicago, a 9. You look, okay, when you go further up north, you'll see a 7, or maybe Fairbanks, Alaska, maybe it's a 6. And then you go way up north, it goes down to a 3. So the sun is clearly stronger the further south you go. So if the sun is stronger the further south you go, the temperatures are going to be hotter the further south you go. This is what people think, and it's true for much of the year. In the summertime, it's different. Before we get there, though, let's just make sure this is understood over here. So it happens to be that a lot of times the ultraviolet light will pretty much be a good reflection of how strong the sun is during normal situations, especially in March and September. In March, and I'll tell you why. It's because March and September is a time when the days are 12 hours long everywhere, and the nights are 12 hours long everywhere, just about. So in March and September, the ultraviolet light, it could very well be, it's going to give you an accurate reading of how strong the sun is, how much sun is reaching the surface, but a better measurement would be solar insolation. This is, the word over here is insolation, as in solar, S-O-L, not insolation. If this episode is being transcribed, it's very possible they're putting in the word insulation with the U. It's not insulation, it's solar insolation. Solar insolation gives you the measurement of how much sun is reaching the surface when the skies are clear for a particular city. So it would make sense if you're in a city where the ultraviolet light, the forecasted ultraviolet light at midday during the peak time is higher than a different city. The place which has the higher ultraviolet light, that's where the sun is going to be strongest. But we're going to see that that is not the case when it comes to the summer. Let's go over to the summer. The summer, we have something that is very complex. We have a new variable that pops up, and that variable is the further north you go, the longer the days are. So now we have a very interesting situation taking place. We have a situation where it's true the sun is weaker at midday. That's true. But there's many more hours of sun during the day. Many more hours of sun. So the question now is, which type of scenario is able to heat the temperatures up quicker? Is it the scenario where you only have a 12-hour day, but you have super strong sun during the hours of 10 to 3, something like that. But you also have 12 hours of night. Or a city which has mediocre sun from 10 to 3, and the mediocre sun tends to generally continue even past 3. There still is mediocre sun, and even if there's minimal sun, the sun continues, and the sun in some places continues for the entire night, for months. Even if it doesn't continue the entire night, for cities which are below the Arctic, the nights are very short. So the question is, what type of place is the sun capable of heating those temperatures up quicker? That's the question. So and the answer is not simple. But the solar insolation chart that the National Weather Service comes out with is a great help. It's a great, great help. And let's think about this. To start, we have two possibilities. The real question over here is, what's stronger? What produces more efficient heating? Do we say that the strength of the sun at its peak during the day, does that produce more efficient heating, or does the length of the day produce more efficient heating? So the answer, however, is both. It depends on where you are. What that means is that the length of the day is the winner, but only to a certain point. The sun has to be strong. It still has to maintain a certain amount of strength for the length of the day to be the winner. For the day June 21st, the length becomes the winner up to about 44 degrees north latitude. I don't have the chart in front of me, and it's possible that I'm a little bit off on that 44 degrees north latitude, but the length is the winner. These are the places which are going to receive the most solar insolation. That's the place where the heating is going to be most efficient on June 21st. If all is even, if all other variables are even, 44 degrees north latitude is going to be the place where there's going to be most efficient heating. Should all places have clear skies, and all places have the exact same air mass everywhere, 44 degrees north is going to be the winner. You also have to realize, if the weather is the same everywhere, all year round, 44 degrees north is going to be the winner. But, even that, there's another twist to throw in over here that's very, very important, because we still have not been able to explain. With this, there's no way we could explain many of the temperatures that we see in Siberia. We could explain some of it. I think Astrakhan is at 45 degrees north latitude, maybe 46 degrees north latitude. So you realize the advantage of that is that although they're not 44 degrees north latitude, the air mass that they are situated in, that air mass will likely include the 44 degrees north latitude area. So this means the efficient heating, the air mass of that heat will go into the 46 degrees north latitude. So it would help explain how things could get hot in cities like Astrakhan, which is in the southern portions of Russia. But let's take this a step further. I think this is going to be super fascinating. What we need to do right now is try to explain how it could be that we can get heat waves very, very far north. This past week, places of Siberia had a heat wave. I believe the latitude generally was in the lower 50s, which isn't, that's not so far up north. But we've had in our past, we've had heat waves. Back in 2020, the temperature actually did reach 100 in the Arctic. In the real Arctic, it did reach 100. So, and I believe it was in Siberia. So we might as well explain how that could have happened. And it could very well be it's going to happen this summer. It could be. Could be it's going to happen again. We want to explain how such a thing could happen. Because we just said the strongest sun, meaning the place which will have maximum solar insolation, where the sun will be able to heat things up the most if you have clear skies and all is even, is going to be around 44 degrees north latitude on the day June 21st. It could be 42 degrees north latitude. It's something like that. It's not going to be the tropics. The sun is super strong in the tropics as well, especially midday. The place you have the highest chance of getting a being sunburned, is going to be way down south. But the place which can get hotter when you have a clear skies is going to be up north. The most ideal scenario, by the way, is to have clear skies during the day and cloudy skies at night, because clouds trap the heat. Water vapor is a form of greenhouse gas, and so it does trap the heat, and then that would be the most ideal. But let's just clear skies, these domes of heat are pretty much the standard way that we get our temperatures up in the northern areas so hot. So here's the next variable. So we said the length of day is the winner, up to 44 degrees north latitude. When you go past 44 degrees north latitude, as strong as the sun is, the length of the day can no longer counteract the strength of the sun in regards to solar insolation. The days can get long, but the sun is at a lower angle in the sky. There's many more shadows in the city, and as long as the day gets, the solar insolation is going to be less. So the heating is going to be less efficient. There's not going to be as much heating from the sun as you go north of 44 degrees north latitude. So it feels like a done case. There should be no reason, there should be no way for excessive heat to develop up in the Arctic. How could it be? How could you have temperatures up there hotter than the temperatures down south? Well, there's other variables involved as well, but here's another twist to the whole situation. The length of the day cannot counteract, as we just said, the strength of the sun when you get north of 44 degrees north latitude on June 21st. That means if you look at the National Weather Service chart, the numbers, which let's just say, here's some numbers to give you an example, whatever units these things are measured in. So on June 21st in Honolulu, Hawaii, it's about 466. I don't remember exactly what it is for a place like St. Louis, but let's say it's something like 470. And in Chicago, maybe it's 472, something like that. When you hit 44 degrees north latitude, maybe it's something like 476. It's all pretty high. And then it goes down. It goes down to maybe 456. I would love to have the chart in front of me, and when I do, perhaps we could update these numbers and get an exact figure, or people listening, if you have an interest, you could look it up yourself on the National Weather Service website. Once you hit the Arctic Circle, which is a little bit past 66 degrees north latitude, I used to think it was 66.5 degrees north latitude. Last year, Wikipedia said it was 66.33 degrees north latitude, something like that. Once you reach there, the days are now 24 hours long, and there's no night whatsoever. At that point, the solar insolation starts to go up again. And at the Arctic Circle, it goes up to 486. 486 at the Arctic Circle. Not only that, it gets higher when you get to the North Pole. So the North Pole, it reaches 526. With the units of solar insolation, 526 is going to be the max, at least in the Northern Hemisphere. You reach 526 at the North Pole. Now, you could ask a question here. The question is, how could it be higher at the North Pole than the Arctic Circle? Both places are getting 24 hours of day. Both places have no night. But the Arctic Circle, the strength of the sun during peak heating is going to be stronger than the North Pole. The Arctic Circle is closer to the sun than the North Pole. So the answer to this is that that's true during the 12, that's true. There's a portion of the day when it's closer to the sun, but there's also the night time. What would ordinarily correspond to night, it doesn't because the sun is up. That is weaker by the Arctic Circle. When I figured it out once, you end up, if you want to figure out the angles, it's actually very easy. What you do is, people who love numbers, they're going to love this part. We're going to go with June 21st. So the sun is coming down at a 90-degree angle for cities which are about 23.5 degrees north latitude or so. What angle is the sun coming down at the Arctic Circle? Let's just say it's 67.5 degrees north latitude. So the way to figure that out is you do 67.5 minus 23.5. You get 67, so you go 57, you do, right, 57, 47, 44.5, 40, I think that's 44 degrees. That's 44 degrees. There's a 44 degrees in terms of the angle. That's the difference between the 90 degrees that's at the northern edge of the tropics to the Arctic Circle. So you do 90 degrees minus 44, and you come up with 46 degrees. The sun is coming at an angle at noon or 1 o'clock at 46 degrees in the sky, which is not so high, but that's what's happening at the Arctic Circle. That's about the strength of the sun during the months of March and September in Chicago. It's about that, because figure during those months the sun is at the equator, that's 0 degrees. Chicago is 40, I believe it's 40 degrees north latitude. So you have a difference. It's 90 degrees at the equator, 40 degrees here. So the difference, okay, 0 degrees to 40 degrees is the difference of 40 degrees in north latitude. So 90 minus 40, it's 50. Okay, so in Chicago, it's 50 degrees. It comes down at a 50-degree angle on March 21st and September 21st. In the Arctic Circle, it's lower. It's coming down at a 46 degrees angle. That's what's coming down. Okay, let's take this up to the North Pole. So the North Pole, you have, the North Pole is at 90 degrees north latitude. The sun is at 23.5 degrees north latitude. So 90 minus 23 is 67. It's about 66.5 degree difference between the northern tropics and the North Pole. So the northern tropics, the sun is coming down at a 90-degree angle. So subtract 66.5 from 90 degrees. You end up with 23.5 degrees. So the sun is coming down at a 20, that's really low in the sky, 23.5 degree angle. The sun is coming down at at noon, 23.5 degree angle, but it's at that angle 24 hours, for a full 24 hours. At the Arctic Circle, it's coming down at a 46 degree angle, but it's only doing that for it's only doing that for a certain period of time, and then it goes down. It doesn't go completely down, but it does go pretty far down. It's 46.5 during the peak, but then it drops to very low. I don't know what the measurement would be. I don't know. We can make up a number. It goes down to maybe 10 degree angle. But at the North Pole, although it never reaches 46 degrees, it never goes that far into the sky. but it never gets lower than 23.5. So, how do we cheshbon this? How do you calculate all this? So amazingly, the National Weather Service has this solar insolation chart, and it tells you exactly what's going on, and it tells you that on June 21st, the most solar insolation is occurring at the North Pole. Now, 23.5 sounds really low. For the sun to come down at a 23.5 degree angle, that sounds really low. But I wanted to say it's pretty much exactly what it's like in Chicago, December 21st. And let's just figure it out right here to get more of an exact number. Chicago, again, is 40 degrees north latitude. On December 21st, the sun is holding at 23.5 degrees south latitude. So, you take 40 degrees and you add 23.5, you get to 63.5 degrees. So there's a 63.5 degree difference between Chicago and where the sun is directly overhead, it's coming down at a 90 degree angle. So 90 minus 63.5 is 26.5. So in Chicago, December 21st, the sun is coming down at a 26.5 degree angle. At the North Pole, it's less. It's only at 23.5 degrees, only at 23.5. The difference would be approximately the strength of the sun in Memphis to Chicago. Memphis, December 20. So the difference would be like Memphis to Chicago. I'm thinking Memphis because these are cities that I've been to, but really it would be probably more like International Falls. Or, Chicago is you have to figure a city that's at 43 degrees north latitude. Maybe Minneapolis is at 43 degrees north latitude. I don't know. So that would be probably similar. The North Pole is probably similar to something like Minneapolis or International Falls, something like that. It's probably similar to that. I mean, figure St. Louis is there's a 2 degree difference in latitude between St. Louis and Chicago, so it's 300 miles. Let's say 300 miles north of Chicago. It's probably less because you have to do it's 300 miles, but the highways, driving is 300 miles. So let's say 200 miles north of maybe Milwaukee, Green Bay, I don't know, somewhere around there. That's okay. Now, so think about if we were to have a December sun, December 21st, and if you were to have that for a full 24 hours, how hot would it be? Okay, so it's a good question. How hot would it be? And there's no night. And let's say you're coming off from summer. Let's say we were to skip. We go from July, we go straight into December, continuous sunshine, low in the sky. The ultraviolet index is a 1. I believe the max is a 1. It never gets higher than a 1. Recently, I think I saw a 2, but it could very well be at the North Pole. It's always a 1 in the summer. That's possible in terms of the ultraviolet index. So 23.5, says the National Weather Service, is high enough in the sky to produce significant heating if you have a 24-hour day, and in fact, that's the winner, and there's no place on Earth that has higher solar insolation than the North Pole on June 21st. But only for June 21st, and for maybe a couple days in each direction. That quickly changes. It's only June 21st where you have the sun at 23.5 degrees north latitude for the full 24 hours, more or less. Once you don't have it for the full 24 hours, things rapidly decline. So we have a situation where you have 2 peaks. As you go north, you have the tropical sun. Tropical sun is always efficient heating. It tends to bring temperatures. There tends to be humidity. At least the areas that I look at, there tends to be humidity. Temperatures tend to go into the 90s. That's a common thing to see in tropical places. Temperatures in the 90s when there's humidity. Temperatures in the hundreds when there's no humidity. As you go north, as you hit 40, okay, So the next question, we're going to delve a little bit deeper here. And here's another wrench, another twist, something to throw in here. So according to what we just said, one could conclude that the hottest temperatures, one might think that the hottest temperature will always occur exactly where the most solar insolation is, according to that chart from the National Weather Service. So, June 21st. Well, it happened back in the heat wave, the historical heat wave at the end of June. It happened. Light in Canada hit 121 degrees. These were all places which were receiving the second most, we'll say approximately the second most solar, the second peak. We have peak number 1 is June 21st. Peak number 2 is at 44 degrees north latitude. I don't know if the Arctic, it could be 44 degrees north latitude is equivalent to the Arctic Circle. We would have to look into the solar insolation chart from the National Weather Service. So it happens. But generally speaking, it doesn't happen. That was something called historical. And the question is, why should that be historical? That should be something that occurs every year. The sun is strongest over there. So here's the reason why it does not occur every year. The reason is because it takes the Earth about 3 weeks, some even say 4 weeks, to respond to the increased heating of the sun. Things are not instant. There's a lot to heat up. So it's kind of like if you go into a room and you put the oven on, or you put a heater on at full blast for 20 minutes. And then after 20 minutes, let's say you walk into the room and it's 55 degrees. You walk into a bedroom, it's 55 degrees. You put a heater on at full blast, let's just say for 10 minutes. Okay, so the temperature goes up to 65 degrees. Or the temperature maybe even goes up to 70 degrees. Then you put it on low. So then the temperature continues to go up. Only by a little bit. But the temperature continues to go up, just it doesn't go up as quickly. 71 degrees, 72 degrees. So what happens is the temperatures continue to go up to about 3, maybe even 4 weeks. If you're by a body of water, it could be longer. It takes the water probably another 3 additional weeks to respond. Some might say, so you end up, the water might respond 6 weeks later. If it's a lake, by an ocean, maybe even 8 weeks. Some say longer. By some places, it's even longer. Some say the ocean water temperatures reach their peak around September 7th for the Northern Hemisphere. So that's far off from June 21st. But here in Chicago, Lake Michigan reaches its peak in August. So it's about 6 weeks later. In regards to the peak heating, it occurs about 3 weeks after June 21st. Maybe 4 weeks, 3 to 4 weeks. Okay, so now that becomes more complicated, and I don't have a comprehensive chart right now to be able to figure out exactly where the hottest, which area for those 3 weeks. You have to take, so at this point what you have to do is you have to add up, let's say 3 weeks is 21 days, 4 weeks is 28 days, so come up with what you have to do is figure out how much solar insolation is within a city. Take the amount of solar insolation per day for 25 days and come up with the average and give that number to the city, and then do that for different cities. So the place which is going to receive the highest solar insolation when you do it that way is not going to be 44 degrees north latitude. It's going to be let's assume it's going to be probably 36 degrees north latitude, because you figure the sun moves about 8 degrees every month. And let's just make sure this is right, because in March 21st, it's at 23.5 degrees. April 21st, let's pretend it's 8 degrees. Let's see if it works out. March 21st, it's at 0 degrees. It's at the equator. By June 21st, it's at 23.5. Let's round it up to 24. You have 3 months. So over a 3-month period, it travels about 24 degrees. So it's about 8 degrees a month. To make it easy, let's just say instead of 3 weeks, let's say it's 4. Let's say it takes 4 weeks for the Earth to respond. And some say 3 weeks. I've seen articles that have said 4 weeks. Some say 3 weeks. But to make this nice and easy, let's say it's 4 weeks. So the sun travels at 8 degrees. So if you're at 36 degrees north latitude, how long of a period of time are you at maximum solar insolation within 8 degrees? Within 8. So, okay, you're 36 degrees north latitude. That's Death Valley, California. So May 21st, that's going to be the place with maximum solar insolation, and July 21st, May 21st and July 21st. June 21st will be the same as April 21st and August 21st. So let's say April 21st to August 21st, they are receiving, if you were to go from April 21st to August 21st, take the average, it's possible the solar insolation will be highest over around 36 degrees north latitude. It might not, because the solar insolation is significantly less when the sun is at 36 degrees north latitude, meaning it might be highest in the world, but it's still less than what it would be on June 21st at 44 degrees north latitude. But the point is that the areas receiving the most solar insolation over a 3 to 4 week period, that's not going to be 44 degrees north latitude. And in order to get the hottest temperatures, you have to be in an area which is receiving the most solar insolation for a 3 to 4 week period. You also have to be under a weather pattern where you have a stagnant air mass, like a heat dome, which happens to be situated over your city. If you happen to have that in a place which is 44 degrees north latitude, it would make sense to say that temperatures could very well reach levels that we've never seen before. Especially if you get that air mass over there long enough. In the southwest Canada heat wave, we came close to that, but we didn't see that. Like in Canada, reached 121 degrees. It did not beat Death Valley's 134 degrees. It didn't. But I suppose you could have a situation, this might sound shocking, but this is just, the way I just explained it, this would be this simple. If you have an air mass that is situated over that area long enough, you should be able to get temperatures higher than 134. Now, you also have to realize, however, that there's no place over there that has an elevation as low as Death Valley. If you're not as low as Death Valley, it will be about 10 degrees cooler. Like Phoenix, Arizona tends to be about 10 degrees cooler than Death Valley. So you should be able to get a temperature of 124. Well, you know what? They got up to 121. That's close enough. So that's pretty much what happened. That's exactly what happened. You got a stagnant air mass over the part of the world which is receiving, if you exclude the Arctic, this part is receiving the most solar insolation ever in the world. So you got a major, major heat wave. We don't even have to come on to the greenhouse. As of now, according to the way I explained it, we don't even have to come on to the greenhouse gases. We don't have to come on to that. You could say the greenhouse gases, some say that it upped the temperature by a couple degrees. A recent article I read said it could up the temperature up to 3 to maybe even 5 degrees Fahrenheit. Okay, maybe yes, the couple degrees sounds more reasonable to me, and that was the couple degrees was said by a meteorologist who lives in the Northwest Pacific, so he's more of an expert on the weather over there. So instead of 121, it would have been 119. But either way, it would have been a freak occurrence. But the freak occurrence makes perfect sense. You could clearly explain it in a scientific way. It has a scientific explanation to it. Okay, now, what would happen if you were to get such an air mass somewhere in the Arctic at around June 21st? Would the temperature be able to reach, let's say, 121 degrees? If you have a city below sea level, which Astrakhan is below sea level, but that place is not the Arctic. It's in Russia, it's not the Arctic. So, what would happen? So, here's the problem. The place receiving the 526 units of solar insolation at the North Pole, that place is all ice. And ice does not absorb heat. In fact, that place is frozen ocean. So, therefore, it's going to be cold there. That reflects 80 to 90% of the sun back to outer space. So, that place is not available to us. We're not going to see hundreds at the North Pole. What we have to do is we would have to go to a place which is in the Arctic, but the ground is able to absorb heat to a maximum level. And it has to be a place which is far enough. It has to be a place that's situated within a heat dome, and there's no part of the heat dome that is touching ice. If you can get that up in the Arctic, the temperatures can get very high. How high? So that, let's say we have Death Valley, the max 134, Lytton, Canada, 121. If you were to get that type of a setup up by the Arctic Circle, so it's difficult to figure out because the air mass as a whole, the air masses could be 1,000 miles large. So the air mass as a whole, there's going to be a lot of the air mass which is not going to be in an area which is getting tremendous solar insolation. Nonetheless, it still can get extremely hot. So I don't know. The places up there are getting more. There are places up there getting more solar insolation than at 44 degrees north latitude, which do not have ice on the surface. But you need a lot more variables to come together. In an ideal situation, I would think you probably could get to 121. But the situation would have to be completely perfect for it to hit 121. But in a, let's say, less than ideal, it's not completely perfect. So whatever the temperatures are, we're seeing that's what it is. So this is how we get temperatures in the low hundreds. I'll tell you one other thing. There's freak occurrences, and these freak occurrences tend to have temperatures 15 degrees warmer than anything that ever happened. For example, the Dust Bowl years. This has nothing to do with... This is just... The world has always been this way. Like, there'll be just this freak occurrence where the temperature is just 15 to 20 degrees warmer than anything that's happened. So you have to see... Let's go back to 2020 and go back to that 100-degree reading that occurred in the Arctic. You have to see, was that a record-shattering temperature? Was the old record like 84? And this was record-shattering? If that's true, then that 100 was the freak occurrence. But if it wasn't record-shattering, then sometime in the future, we will see a freak occurrence, which is going to produce temperatures in the 110s in portions of the Arctic that have no snow and are under a stagnant air mass around June 21st. And the air mass is not touching areas of snow, and you have clear skies. There's at least one other thing that I want to point out that I think is important to point out. But let's just let that sink in for a minute before we go on to the next segment. Okay, we're going to go a little bit deeper over here. This whole thing of the records is different than the months where we see the highest average temperature. The hottest month in the northern hemisphere, places north of the tropics, generally speaking, is the month of July. Okay, at the same time, when you go up north, the places which have the highest chance, the time of the year that has the highest chance of seeing extreme temperatures is going to be June 21st. Right around June 21st, or very close to it. We see that. The Pacific Northwest, we've been seeing that a lot. But in the Arctic, we also see that. Even though July, in these cities, July might be the warmest month when you average it all out. But in regards to extreme heat, the thing is, if you were to get a stagnant air mass up in the Arctic around July 21st, the solar insolation July 21st is much lower than June 21st, and I don't really think anything could happen. Especially by August. I remember by the end of August already, things go back to normal. The highest solar insolation is occurring down south. It's no longer up in the north. And by July 21st, it's close to that. So there's really not that much solar insolation up there. There's still might be more up there than down south, but realize a lot of cold air aloft. There's a lot of things that has to be heated. So this really has to happen right around June 21st. Generally speaking, there is somewhat, at least, of a progressive weather pattern. Things are moving, and when things are moving, so we're not going to be seeing extreme heat. Therefore, the average temperatures are highest in the month of July. But in a situation where the air mass becomes stagnant, so then, and it's around June 21st, that's when we're going to see the most extreme heat in the northern latitudes. We're now going to address a question that perhaps many people here have. Here's the question. We just explained, took a lot of time to explain all this. Maybe there might be people who have an interest in this, maybe not. And not maybe not. The world has billions of people, and for sure there are those who are interested in this. But there's a question that many people are going to ask. And the question is, you're going to say, okay, I just heard this whole thing about why we get such hot temperatures up north, and it's all connected to solar insolation. But I read in the paper that it's connected to greenhouse gases and things similar to that. They don't mention anything about solar insolation. So what's going on here? I like to say greenhouse gases instead of the other terms. So what's going on here is like this. There's no question the main thing at force is the solar insolation. We're not going to get temperatures like this in the month of March, January, February. It doesn't matter how many greenhouse gases there are. So, and the main thing actually is it's a tremendous, if you think about it, it's a tremendous wisdom. The creator of our world, this in his infinite wisdom, made the world in such a way that even places up north can receive a summer. And it's just amazing how by tilting the globe, by making the world round and tilting the globe in such a way,
what ends up happening is, even though these cities are not getting direct sun, but they're still getting a high level of solar insolation, so they still receive the summer. Realize, however, if skies are cloudy or it's raining, which happens a lot, so that kind of destroys the whole thing, and that's the main reason why the average temperatures are not that high when you go further up north. The greenhouse gases will be able to explain at least one thing, and according to many, two things. So the one thing people say, scientists say, is that the greenhouse gases, they don't produce these stagnant air masses, but once we have the air mass, the temperatures could be increased by 1 or 2 degrees, or we said earlier, according to some, perhaps 3 to 5 degrees. That sounds like a lot. We also have scientists who say that the greenhouse gases themselves are causing these stagnant air masses. So to that, the question is, well, hold on. That's complex, and that's the real issue. I mean, these heat waves are not just 1 or 2 degrees warmer. It's the very fact that there is a heat wave. So not all scientists agree, from the research that I've done, and also from the research that I've done, it's not actually the increase in greenhouse gases itself that would be causing this. It's the fact that it's disproportional. It's the fact that the Arctic is warming at a quicker pace than other areas. And the only way I can understand it is if certain parts of the Arctic are warming at a different pace than other parts of the Arctic. So I would think that's the case, because let's say the areas of land in the Arctic, so as the permafrost melts, so you have the greenhouse gases being released from the ground. The parts of the Arctic which are ocean, perhaps there's some other greenhouse gas being released, but it's different. So if you have a lot of warming up in Alaska, so the jet stream tends to stay north of the warmer areas, and then so you have a bulge in the jet stream, and a bulge produces a dip in the jet stream right next to it, and then dips produce a bulge in the jet stream, which is called ridges and troughs. So you'll have a ridge in the jet stream over Alaska, then a trough over just to the east of that, then a ridge. And those are the types of things that produce, first of all, storms, especially in the winter, and you could get a stagnant air mass in the summer. That's what we've been seeing in recent weeks. The other thing to point out is that even if you don't say that, when the contrast in temperatures, the jet stream gets its energy from contrast in temperatures. As that contrast in temperatures becomes less, the jet stream weakens, and when the jet stream weakens, the progressive weather pattern weakens. The air masses move slower. So if there's temperatures are becoming warmer up north quicker, so then the temperatures become more similar. There's less of a contrast, so the summertime jet stream kind of just weakens out, and so the air masses become slower. So that's one of the theories, or that's some things that scientists say. We're going to go on to speak about some more excitement, and then I'll leave everyone off, and have a wonderful day. Thank you for your interest. Thank you for listening. For right now, we're just going to put on Friday's short episode, and perhaps we'll have another segment later on. There's a lot of really big news that's going on in the weather. The first thing that's very apparent is that the El Nino is official right now. It developed earlier yesterday, and the National Weather Service says that it came about a month early. It's also stronger than forecasted. As of right now, the El Nino is heating up the ocean waters in the Pacific Ocean, but it's happening by the equator, which is south of where hurricanes develop. Therefore, it is not expected to increase the number of hurricanes for this season, perhaps maybe next season. That's the latest news from the National Weather Service. The effects, the impacts that an El Nino will have and could have for this upcoming year is definitely an episode in and of itself, but we now have other things which are going on as well. We're going to briefly discuss that. These are pretty much the headlines, and God willing, we'll have an episode or more for early next week. Stay tuned. The heat is just so intense. There's so much going on in the world right now with the air quality, not just from the wildfires in Canada, which continue. There's also a volcano which is erupting. It's down in the Hawaii area. And this volcano is occurring at a much lower altitude than usual, which is causing a lot more air pollution. It's going right into the surface air, which is really producing a very contaminated air, very high level of pollution. That's something to talk about, that these things, each one can be made into a separate podcast, a separate episode on the podcast. The real story right now, well, right before we get to the real story, we'll just mention that San Juan, Puerto Rico continues to have excessive heat. You know, how often do you see excessive heat warnings in effect for San Juan, Puerto Rico? I don't know if I've ever seen it before. Maybe once. I vaguely remember seeing it once, but this is just continuous for the month of June. We have a stalled jet stream. Everything is stagnant. That's what's been happening over the past month, and a stagnant situation for everything. Just all these everything is stagnant. Nothing's moving, and therefore you have high pressure, which the high pressure over the San Juan, Puerto Rico, that was stagnant. High pressure produces sinking air, which prevents thunderstorm development, and the sun just continuously gets things hotter and hotter. It's really the high dew points which are really something phenomenal. Temperatures are in the low 90s for highs. At night, you're probably getting down into the low 80s. Occasionally, temperatures go into the mid-90s. On normal highs for San Juan are 89 degrees, and record highs are right around 92 to 93 degrees. So when a temperature hits 93 or even 94, that's a record. If you look at the heat indices, you'll see at times the heat index for parts of Puerto Rico has gone up to 125 degrees. That's based upon just the humidity alone. We're dealing with dew points. I don't know how that happens, because if you look at the charts that I see dew points in the mid 70s, but clearly dew points are in the mid 80s. You have to have a dew point in the mid 80s to be getting something like that. You can't, even a dew point of 80. A dew point of 80 would bring a heat index probably up to about 110, 113 degrees. That's been the norm. Dew points in the low 8. The heat indices in the low 110s, that's been the norm. So you have to figure whatever charts I've been looking at, they're not accurate. The dew points are based upon the National Weather Service, their warnings, which are continuous. Even the National Weather Service reports of the dew points, as we pointed out in the past, the things don't match up. But it does seem clear that the real reality is the excessive heat warning material. That's what's actually happening. And the data which contradicts that part is where the inaccuracies are. I don't know why we're having dew point maps of temperatures in the 70s, dew points in the 70s, or, it's dew points in the 70s and highs in the low 90s. That's Miami Beach material. That's not excessive heat warning material. The big story right now is a brutal Siberian heat wave that has developed amazingly. Temperatures are well into the hundreds over a part of Siberia, and this is just the beginning. We're going to have more to say about this on Sunday, God willing, and right now we're out of time. but this is a big story here, and it's there's just so much. There's so much, and so stay tuned to those that are interested. This is not something that you're going to want to miss. I wish everyone a wonderful Shabbos. You've been listening to the podcast Weather with Enthusiasm. The following trailer was updated June 7th, 2023. Special guest on our show. What is your name?
Temperatures going into the low hundreds for the next 3 days.
Holy cow!
The Blackberry Winter, that comes up every year here in the Midwest on May 11th.
Several additional feet of snow is expected by Monday morning.
This was in the forecast from a week ago, and the National Weather Service is finally acknowledging it today. Conditions are favorable for the development of an El Niño. We're going from one extreme to the next extreme. Despite the fact that it's 113 during the day and 46 at night, you could still do a little dance. Recorded temperatures during heat bursts have reached well above 104 degrees.
Oh my gosh.
Google Weather with Enthusiasm, and they're all going to come up.
Meteorologist Simcha left. Weather with Enthusiasm is his podcast.